Okay, let's see. Okay, I'll speak softly. So it's really a great pleasure to be at StanCon, and it's a bit of a relief for me to finally be able to say, yes, the embedded Laplace approximation is now in Stan. People have been asking me about this for years, and it's been years in the making, and it's thanks to the fantastic efforts of a few collaborators, including Steve, Aki, and Brian. They're all here, and you can speak with them. And I want to start by thinking a little bit about the landscape of statistical software. So I think we have software like Stan, which are general purpose, and as a main inference engine, they use Markov chain Monte Carlo, which work on a very broad class of models. But then you have other software that have kind of taken a different approach, which is to focus on a certain class of models, in this case, latent Gaussian models, and then use a specialized inference algorithm. Alors, why use a specialized inference algorithm? There are really two reasons. One, it's that MCMC oftentimes struggles with latent Gaussian models. And the second reason is that a specialized algorithm can take advantage of the specific structure of the model in order to achieve faster inference. In fact, if we look at the seminal paper by Harvard Rue and colleagues that came out in 2009, where they kind of built the integrated nested Laplace approximation, which would become the foundation of the INLA software. Their observation is that for the models they were looking at, MCMC could take hours or even days to run, whereas they were able to get accurate inference in a matter of seconds or minutes. So this should at least intrigue us. Now keep in mind this was written in 2009, so before Stan came out, but nonetheless, almost 2 decades later, INLA is still being widely used, and so is TMB, for example. So today I want to talk about what are latent Gaussian models and why you should care about them, what is the embedded Laplace approximation, and how do we use it in Stan. And finally, given that I've told you that the embedded Laplace is a specialized algorithm, why do we want to put it in a general purpose software like Stan? So a latent Gaussian model is essentially a multi-level model where the latent variable, so for example, as defined by Paul, is normally distributed. I'll give you a running example. This is a disease map. By the way, does anyone know which country this is? No? Not Scotland this time. But it is a disease map of alcoholism, so maybe that would have been a reasonable guess. This is actually a map of Finland. And what we're doing is we've kind of broken it up into counties, right? That's what the different pixels represent. And so your likelihood factorizes, and at each county, you have a mortality count, right? And then you have a latent variable theta I, which kind of gives you the expected mortality count with some adjustment delta I. And because this is count data, the distribution is going to be a Poisson distribution, right? And then the other ingredient is that these theta i's, which each correspond to a county, are going to be distributed according to a multivariate normal, right, with a covariance given by a squared exponential kernel. And that squared exponential kernel, what it does is when counties are geographically close to one another, they're going to be strongly correlated. When they're far away, they're going to have a weak correlation, right? And that allows us to do partial pooling in a rather informed manner. This prior covariance matrix is parameterized by a hyperparameter phi, which controls the strength of the correlation as a function of geographical proximity and also the overall variance. Right, so that's going to be our running example, but actually this structure of the latent Gaussian model is extremely common. Right, so other examples could be Gaussian processes. In fact, this disease map is a Gaussian process. But really, any hierarchical model that I've ever fitted for applications or for illustrative examples has been a latent Gaussian model. We almost always use multivariate normal priors. Right? Another example is when we do sparsely inducing priors, right? These also end up being latent Gaussian models. So it's a very, very broadly applicable class of models. And so, of course, our goal is to get some approximation of the posterior distribution. And the challenge here is that these latent Gaussian models are very prone to create tricky geometries. Right? So this is Neal's infamous funnel, right, which is due to the interaction between the latent variables and the hyperparameters. And the problem with this kind of distribution is that you have an unbounded density that actually goes to infinity as you go down the neck of the funnel, and an uneven curvature. Alors, if I wanted to fit, let's say, the disease map with MCMC, I can do it. Right? I just have to take a few steps. Now, first, I need to find the right parameterization. In particular, I need to do what's called a non-centered parameterization. Right? And then I have to do a little bit of tuning, so increase this parameter adapt delta, which is going to make HMC take smaller step sizes. Right? Steps 1 and 2. The third step is I have to wait for some time. Right? But at least for this example, I can get it to work. So now I want to propose an alternative approach. Present an alternative approach, which I'm going to call two-step sampling. And the idea of two-step sampling is that actually, instead of tackling head-on the joint distribution, I'm first going to sample from a marginal posterior distribution, right? P of phi given y. And then, once I've generated samples, phis, I'm going to use those sample phis to generate samples of theta, based on this conditional posterior. And now the advantage of that is that it avoids dealing with the joint distribution. Neither the marginal posterior or the conditional posterior exhibit the kind of complicated geometry, such as the funnel. Right? But now the question is, how do we actually compute this marginal distribution and this conditional distribution? Okay, so here's a proposition. The marginal likelihood is simply given by this ratio. The terms on the top, that's just my likelihood and my prior on the latent variable, so I have access to them. And the terms on the bottom, that's just the conditional posterior that I need to estimate anyways. Right? The proof of this is Bayes' rule, and you rearrange the terms. So if any one of you gets bored during the talk, you can convince yourself of this fact. Right? So now I've reduced my problem of estimating two densities to the problem of estimating a single density, which is this conditional posterior. Fun fact, this equation holds for any theta, right? We're going to be plugging in the theta that maximizes the conditional distribution. That's what people do traditionally. But recently there was a paper by Lai, I'll mention it again at the end, where they realized that you can plug in other values of theta and get some very interesting results when you do that. And then, once I've approximated the marginal likelihood, P of y given phi, well, I have the prior on phi, so I can recover the posterior using any standard inference procedure, for example, MCMC. Okay, so now we still need to approximate the conditional posterior distribution, and this is where the Laplace approximation comes into place. Now, what is the Laplace approximation? There are a lot of different ways to introduce this. I'm going to present it as a second-order Taylor expansion of a target distribution, right, log pi of x, around its mode. Right? So let x star be the mode of pi of x, then this is going to be my second-order Taylor expansion. Okay, how does this help me? Now I just have a bunch of expressions. Well, let me convince you that this is actually a normal approximation. Right? How do I do that? Well, first of all, the first term is just a constant. So I can ignore it. I'll be renormalizing anyways. The second term goes to 0, because at the mode, the gradient is equal to 0. And now you're left with a quadratic term. And if you stare at this term, you'll realize that this is actually what the log density of a normal distribution looks like. Right? In particular, it's a normal approximation centered at the mode x star with a covariance that is driven by the Hessian. Right? Actually, what's going on here is that it's a normal approximation that matches the mode and the curvature of your target density. And so to know whether this approximation is good, we need to characterize what happens to the higher order terms of the Taylor expansion that we've ignored. Right? And it turns out that there's a lot of work in the statistical literature on that. And what was found is that if your conditional posterior has a normal prior and your likelihood is log concave, then you get very accurate Laplace approximation. Right, so what are examples of log concave? Likelihood normal. In fact, if it's normal, then the approximation is exact. So because of conjugacy. Poisson, which is the case we're interested in the disease map, but then you have a number of other standard distribution. What's an example of a common distribution that is not log concave? Student T, right? And then there are a bunch of other distributions. Alors, in practice, even if you violate log concavity, you still seem to get reasonable approximations. So there's a bit of an open question to really characterize what are the distributions that break this Laplace approximation. So let me summarize. Actually, before I summarize, let me demonstrate how now do you implement this in STAN, right? So I have two-step sampling. First, I need to sample from the marginal posterior. And so now what I have is a function that lets me increment target, so the joint distribution, by the marginal likelihood. That's the function Laplace marginal. What it takes in is a user-defined likelihood function, so I have to specify what my likelihood function is. Then I pass in as tuples the arguments that go into the likelihood function. Then I need to specify my prior covariance function for my multivariate normal prior. And once again, I pass in the arguments that go into the prior covariance. There's another argument here called Hessian block size. It kind of gives you control over the sparsity of a Hessian that you have to compute. I'm not going to talk about this. Hopefully, it's well documented in the user's guide. Okay? That's the first step. The second step is now I go to generated quantities, and I have a function that lets me samples thetas from my approximation to the conditional distribution. It's called Laplace latent RNG, and it's exactly the same signature. Right? The signature is identical. So now I can do my two-step procedure. So let's summarize a little bit. I have my latent Gaussian model. I can either do sampling on the joint distribution head-on, right? And if I do that, I can use MCMC, maybe with a non-centered parameterization and some careful tuning. But I could use any number of other algorithms. For example, I could use Pathfinder variational inference. Right? Why not? Maybe it works. Or I could do a Laplace approximation. You try this with STAN, you get an error message that tells you it didn't find the mode, which is fair enough because the mode doesn't exist. Right? This is an unbounded distribution. Okay, now I can do two-step sampling. And here, once again, I have a bunch of options for how I'm going to sample from the marginal posterior. I can do MCMC, I can do Pathfinder variation and inference, or I could do Laplace approximation. Now, in fact, a software like INLA, right, both does a Laplace approximation of the conditional posterior and then a Laplace approximation of the marginal posterior. That's why it's called integrated nested Laplace approximations. You actually have two Laplace approximations. Don't ask me which one is integrated and which one is nested. But the point is you have two Laplace approximations. Right? And once I've drawn my samples from the marginal posterior, then I can draw my samples from the conditional posterior. Right? Everyone on board? I see some nods, so I'll take that. All right, so how well does this actually work? So this is, again, for the disease map. I'm just looking at a few of the parameters. And what I've done is I've taken MCMC to be my golden benchmark, right? And I'm plotting the posterior median and then the 90% interval, and I've recentered everything at 0 and rescaled it. Okay, so ideally, we want to recover what we get from MCMC here. This is MCMC plus the embedded Laplace approximation, right? So I use MCMC for the marginal posterior, and then I get samples of theta with the Laplace approximation, and you see that you have near perfect agreement, right? Any disagreement is going to be within Monte Carlo standard error. Okay, this is Pathfinder plus embedded Laplace approximation. Once again, you get pretty much near perfect agreement, right, between the two algorithms. This is Laplace plus embedded Laplace. So this looks pretty good. If you're picky, you might notice that actually Laplace isn't capturing the heavy tail behavior of the hyperparameters, right? But otherwise, it's doing a pretty good job. And then this is Pathfinder on its own. So this time, the estimates are all over the place, and in fact, you get a phenomenon of posterior collapse where the posterior intervals almost collapse to zero with pathfinder variation inference. And the point I want to make is that a lot of these fast approximate algorithms will really struggle when you throw them at the joint distribution, but actually the marginal posterior itself can be really well behaved and really amenable to those fast approximations. All right, so let's compare runtimes. So this is not going to be a sophisticated analysis of runtimes. I'm just going to look at, I take the algorithms off the shelf and I use the default, right? So hopefully reproducing the user experience, right? So I use the default tuning and then I see how long does it take to run. And these are the runtimes that I get. MCMC takes 12 hours. If I do MCMC plus an embedded Laplace, I get the time down to 2.5 hours. If I use Pathfinder as a backend, which is still reasonable, I get my runtime to 9 minutes. So even with the recent developments that we've seen with MCMC and gradient-based MCMC, we still seem to agree with that claim from a few years ago that we can get models that take hours to run in MCMC to run in shorter time. With we've cheated a little bit. We've used Pathfinder as a backend, which didn't exist at the time. Okay, so why would we want to build the embedded Laplace in Stan? Now, one thing is, with Stan, we have scalable automatic differentiation. Right? And this is a little bit due to some of the innovation that we've done, where actually you can really compute the embedded Laplace approximation and its gradient, not only in cases where the hyperparameters is low dimensional, but you can push that to cases where phi is high dimensional. Right? Now, I want to say that TMB also has good support for scalable autodiff, and the INLA folks just recently put out a paper. So, maybe we'll see some of that in INLA as well. Okay, Stan gives me an expressive programming language, which means that I can actually specify very sophisticated priors, potentially ones where phi is high dimensional, right? An example is horseshoe prior, right? I can specify any likelihood that I want with Stan. That doesn't mean the approximation is always going to be accurate, but you get this great power, which means you have this great responsibility, right? And then I have flexibility on how I actually do inference on the back end, right? I'm not constrained to only do Laplace approximation on the back end. I could do Pathfinder, or I could do MCMC, or anything, since I have access to bridge Stan. So now I have a lot of flexibility, but then there are questions about what are the back-end algorithms that are going to be accurate or not. So I'll very quickly give an example where we kind of take advantage of the flexibility afforded by Stan. This is a genetic model where essentially we have a horseshoe prior, and the dimension of the hyperparameters now is no longer 2, it's something that goes all the way to 6,000, almost 6,000. Right? Not only that, the marginal posterior is multimodal. Right? And that's why you can't just use a single mode approximation as a backend, you really need something more sophisticated like MCMC. And so HMC plus embedded Laplace captures the multiple posterior modes, but it does introduce a bias, right? You can see that the histograms are not exactly lining up. I would argue this bias is manageable. Why? Because if I look at the downstream scientific tasks, right? For example, covariate selection or prediction about whether a patient develops cancer or not, I actually get pretty good agreement between full HMC and the Laplace approximation, and HMC with Laplace approximation. The one turn down that I would say is that for this particular model, you actually don't really get a meaningful speed up from using embedded Laplace, right? There's a more complicated version of this model where you get more speed up, but I want to drive home the point that you don't always automatically get a ton of speed up, right? Well, with that said, what are we missing? We have limited support for sparsity calculations. That's something TMB and INLA really excel at. That's not something we have in Stan. Right? So we have by no means made INLA or TMB obsolete. Let me be absolutely clear about that. And we don't quite have automatic diagnostics. So you know how you run Pathfinder and then it runs a diagnostic automatically? I think we should try and get that for embedded Laplace. So this is an area of ongoing research. I'll just plug in recent work by Jilin Lai from the University of Massachusetts, who had this awesome realization that you can think of the embedded Laplace approximation as a kind of importance sampler, and you can come up with a way to make that importance sampling estimator unbiased. And then you can use a number of other strategies to reduce the variance of that estimator. Right? And this has led to the corrected integrated Laplace approximation. We have another bunch of tools like Pareto smooth importance samplings that I think can go a long way. With that said, I invite you to try it, to use the documentation and the case study that we've put out, and to tell us how it goes on the Stan forum and probably with some GitHub issues as well.
All right, who wants to do the question before lunch?
Thanks. This is really great work, and I think it closes one of the important gaps we had in Stan. So I'm very happy to see it done and how it's done. The interface looks really nice. So I was wondering, since before I talked about this distributional models, what happens if we have like latent variables on both the standard deviation and the mean of a Gaussian distribution? Is it probably not log concave? I have no idea. What would I do in this case with Laplace approximation?
Yeah, in fact, one of the test problems that we used had exactly this behavior. You can try it, and sometimes it works, but there's no guarantee that it works universally. But the amazing thing is, with the flexibility of the UI that we've put together, and that is thanks to like fantastic work by Stan developers and Steve, for example, right? We now have the sandbox to really try this and push this a little bit further. So I can't guarantee that it's going to work, but at least as a researcher, I'm excited that we can try it. And there are some precedents for doing that. So I think it will work in some cases.
Thank you.
All right, thanks a lot. It was a wonderful session with great presentations, and I hope that this all has inspired you to work on the topics that were presented today. And now we'll have a quick announcement about lunch, but once more for all the speakers, please, if you can